All right, guys, so this is 6.1 part 2, and we're looking at solids of revolution, volume by cross-sections that are washers. So I think it's wise to look at the two pictures, and if we look at the first picture here, we see this figure where there's like a hole bored through it. So there's a hole right in the center, so it kind of looks like this. I'm trying to give you guys an image of what's going on here. Okay, and then the other picture, if you look at it, here's the top. So it has a hole bored through it. So we can find the volume of things like this by using washers. So let's talk about what is a washer. So a washer is exactly what you think of when you are putting something together and it has a washer to protect the wood. So here's an example of what a washer looks like. So there's an inside radius and then there is an outside radius, okay? And so when we find the area of a washer, we're going to use pi times the outside radius squared minus the inside radius squared, okay? So to find the volume of the solid of revolution, we're going to take volume equals integration of the area, and the area is pi times the radius of the outer washer squared minus the radius of the inner washer squared, d something. Okay, so it just depends on what axis you're revolving around. That's going to affect if you have dx or dy here. Okay. So with these, you're going to have to do some work. And before I continue on, I just want to show you what is the difference between R inside and R outside. So I drew a picture over here of a washer. And so the one on the right, the radius stems from the center clear out to the very edge of the washer. That's going to be the radius of the outer washer, so RO. On the next one, just right beside it, I am doing a washer from the radius to the inside. This is going to be the radius of the inside of the washer. Okay, so outside is the outer edge, and inside is the inside edge. Okay, this is going to be very important when we figure out what is the radius, because we're going to have to square that. So we go on to state that let R be a region bounded by y equals f of x, y equals g of x, where x equals a to x equals b. Okay, so that's going to be your lower and upper limit. And f of x has to be greater than or equal to g of x, because remember, we have like a washer that's going to develop, so it has to be that way on the interval from a to b. So revolving R about the x-axis forms a solid of revolution. Cross-sections perpendicular to the x-axis are circular washers with the area a at x equals pi times r, the radius of the outer washer minus the radius of the inner washer squared. So basically we take pi times the function at x squared minus the function at g squared. Then the volume of the solid is given by volume equals the integration from a to b of pi times r outer squared minus r inner squared dx. Okay, so once again, if r outer is a function at x squared and r inner is the function at g at x squared dx. So we get this picture here. So here is a, here is b, r inner is going to be this, and r outer is going to be this. Okay, so R outer is the function f of x, R inner is going to be the function g at x. Okay, so let's check out this next bit. 2, let R be a region bounded by x equals f at y, x equals g at y, where y equals c to d. F at y has to be greater than or equal to g of y, because remember, we're dealing with a washer here, on the interval from c to d. Revolving R about the y-axis forms a solid of revolution. Cross sections perpendicular to the y-axis are circular washers with the area. Area at y equals pi times r, the radius of the outer squared minus the radius of the inner washer squared, or which equals pi times f at y squared minus g at y squared. Then the solid of revolution is given by the volume equals the integration from c to d of pi times r outer squared minus r inner squared dy. Okay, so once again, if we look at the figure, my outside function is f at y. So my radius is going to be from the axis of revolution out to that function. So that's why r out is f at y squared. Okay, r in is going to be the inside function. So this inside function is g at y. So the r inner, the radius of the inner washer is going to be g at y squared dy. Okay, so example 3 says, find the volume of the solid formed by revolving r equals y equals tan x, y equals 1, x equals 0 about the x-axis. So once again, you can't do these unless you draw it out. So let's draw something. I'm going to make it kind of big. So we know that tangent looks like this. Okay, and then y equals 1, that's going to look like that. And x equals 0 is the y-axis. So basically I have this little figure here, and I also know that the axis of rotation is about the x-axis. So I know I'm revolving around. So now I can kind of draw in my ghost function so that I can see kind of, what the heck is going on with this. And I'm going to highlight the other side. So that's my figure. So in order to find the volume of that figure, because there's kind of like a hole in the center, I'm going to use a washer. Okay, so there's like continuous washers that are going down towards the end. Okay, so I know my washers are perpendicular to the x-axis. So since my washers are perpendicular, or vertical, if the washers are vertical, then we know that we have to integrate in terms of x. Okay? So I'm going to set up a generic form. I have to find the upper and lower limit because I don't know them right now. I have pi times r outer, the radius of the outer squared minus the radius of the inner squared dx. Okay, that much I know. Okay, so let's go ahead and work on r outer and r inner. So the outside function, and if I draw this bigger, we'll just look at this really quickly. So I'm just enlarging this so we can see it. Okay, so once again, I'll draw that washer in. The radius of the inside function is going to be from the x-axis to this function here, which was tangent x. Okay, so let's take care of r inner first. So r in. So once again, the radius is from the function. Remember, this was y equals tangent x. So we have tangent x minus 0 because that's the x-axis itself, right? So r inner is going to be tangent x. Okay. Now remember, we need r in squared. So I have to square tangent x. So r in squared equals tangent squared x. Okay. Now let's work on r out. So once again, I'm just going to enlarge this really quickly. So our shape looks like this. I know this isn't perfect, but just bear with me a sec. So here is the axis of revolution, x-axis. So what do we have here? I'm looking for that washer again, so I'm going to draw that out really quick. So the washer, I'm looking for the radius. So the radius is from the x-axis clear out to the edge. So I need this function here. That's my outside function. The outside function is y equals 1. So for r out, I have y equals 1 minus the x-axis, which is 0. So r out equals 1. Okay? So we need r out squared. So if I square 1, I get 1. Okay? So my next step, after I find r in, which I'm going to go ahead and circle and r out, I now have to do this piece here. R out minus R in. Okay, so I'm going to do that on the next page here. Okay, so I'm looking for R out squared minus R in squared, because remember we're trying to do the integration here. Okay, so let's go ahead and fill that out. So I don't know upper and lower limits yet. But I do know that R out was 1 and R in was tangent squared x dx. All right, so now let's find the upper and lower limits. So once again, I'm going to quickly draw our function again. Here's the x-axis, here's the y-axis. Here's tangent x, here's y equals 1. So I have this going on, right? And remember, I want my x values. So I want the intersection point here, and I want the intersection point there. Okay? All right, so to find those intersection points, I'm going to do the upper limit first. So the upper limit is this one. So upper limit. The upper limit is where y equals 1 and tangent x intersect each other. So let's set those equal to each other. So where does tangent equal 1? And hopefully you said pi over 4. This is my upper limit. Lower limit. Okay, I'm looking at this and I have y equals tangent x, and I also have y equals 0. So where does tangent x equal 0? Hopefully you guys said 0. So I have my upper and lower limits, so let's go ahead and plug and play. So the upper limit is pi over 4, the lower limit 0, and I have 1 minus tangent squared x dx. And we make sure we have pi in there. We've got a problem here, and the problem is I can't integrate tangent squared x. I don't have any rules for that. So I have to be clever. So if you guys remember Pythagorean identities, remember that tangent squared x plus 1 equals secant squared x. And by the way, secant squared x, I have a rule for. So if I isolate tangent squared x, I get the statement that secant squared x minus 1 is equal to that. I'm going to use substitution. So I'm going to substitute in secant squared x minus 1 in for tangent squared x so I can integrate this. So when I do that, I have 0 to pi over 4 pi times 1 minus secant squared x minus 1. So that's what I did the substitution so that I can integrate it. Okay, so if I distribute the negative sign, I get 1 minus secant squared x plus 1. So 1 plus 1 is 2. So I get 0 to pi over 4 pi times 2 minus secant squared x dx. Okay, my next step is going to get and move pi outside of it. I'm going to integrate it, and then I'm going to evaluate it at the upper and lower limit. Okay, all right, to integrate it, I'm going to keep pi on the side. I'm going to integrate the negative secant squared first. I'm going to kick the negative out. And I know the integration of secant squared x is tangent x. Okay, then I have to integrate the 2. So it's going to be a positive 2 pi x, okay? And that's distributing the pi. Now I'm going to evaluate this guy from 0 to pi over 4. So what may be easier when we evaluate it is to kick the pi out, okay? And then when I kick the pi out, I'm going to do f at b minus f at a, and then I'll put the pi back in at the end, okay? So I'm going to leave pi over here. So f at b is going to be evaluate the function. And by the way, the function, if I take pi out, is negative tangent x plus 2x. So I get negative tangent at pi over 4 plus 2 times pi over 4 minus f at a, which f at a is going to be negative tangent at 0 plus 2 times 0. Okay. So let's evaluate this. So pi is hanging out there. Tangent of pi over 4 we said was 1, so this becomes negative 1 plus pi over 2. That's what I get when I multiply 2 times pi over 4. And then the rest of this just becomes 0, because tangent at 0 is 0, and 2 times 0 is 0. So that pretty much goes away. So here's what I get. I get negative pi plus pi squared over 2. Okay, and that's my answer right there. That is the volume using the washer method of example number 3.